Have you ever wondered how we describe, like, the tiniest particles in the universe?
Yeah.
I mean, we can't just pull out a ruler and measure an electron, right?
Right. Yeah. It's a fascinating challenge. And that's where this whole concept of a quantum state comes in, you know? It's a totally different way of thinking about particles compared to our everyday experience.
So instead of just saying, like, here's the electron and it's at this exact point and it's moving at this speed, like, we need a whole new language to talk about the quantum world.
Exactly. Yeah. In quantum mechanics, we can't know both the position and the momentum of a particle with absolute certainty at the same time.
Whoa.
It's kind of like trying to nail down a shadow, you know? The more you focus on one aspect of it, the more elusive the other one becomes.
Okay, that's already kind of blowing my mind a little bit.
Mm.
So how do we even begin to describe these quantum states then? Like, what kind of mathematical tools do we even use?
Well, there are a couple of key approaches, and they kind of depend on what aspect of the particle we're most interested in. So one way is to focus on the particle's location in space.
Okay.
And we call this the position representation.
So if I wanted to know where, like, an electron might be found inside an atom, this position representation would be the way to go.
Exactly. In this representation, we use something called a wave function, and it basically gives us a probability map.
Okay.
It tells us the likelihood of finding the particle at any given point in space.
So it's not about an exact location, but rather like a cloud of possibilities.
Precisely. It's like, imagine you have a heat map, and the hotter areas represent, like, higher probabilities of finding the particle.
That makes sense. But you mentioned there was another way to describe these states, right? One
Right.
that doesn't focus on location.
Right. If we're more interested in the particle's motion, its momentum, we use the momentum representation.
Okay.
And just like with position, we have a different kind of wave function for this, and it tells us the probability of the particle having a particular momentum value.
Okay, so position is like a snapshot of, like, where a particle might be, and then momentum is about capturing how it's moving.
Exactly. Think of a free electron just zipping through space, you know?
Mm-hmm.
Its position might be very uncertain over time, but its momentum could be constant and very precisely known.
Right.
This is where the momentum representation shines.
I'm starting to get the sense that these two representations, position and momentum, are like two sides of the same coin, you know?
Yeah.
It's like they're different ways of looking at the same quantum reality.
That's a really astute observation, and here's what makes it even more interesting.
Okay.
These representations are actually connected in a really profound way.
Interesting.
We can mathematically translate between them using something called the Fourier transform.
A Fourier transform. That sounds pretty complex. Is there, like, a way to understand this without having to, like, dive into all the heavy math?
Yeah, think of it like translating a book from English to French, you know?
Okay.
The content of the story remains the same, but it's just expressed in a different language. The Fourier transform does something very similar. It allows us to express the same information about the quantum state, whether we're speaking the language of position or the language of momentum.
So it's like having a universal decoder ring for quantum mechanics.
That's a great analogy. And this ability to switch between these representations is really powerful.
Okay.
It leads us to one of the most fundamental principles in all of quantum mechanics, the Heisenberg uncertainty principle.
Oh, I've heard of that one. It's the idea that we can't know both the particle's position and its momentum perfectly at the same time, right?
Exactly. And this principle directly emerges from the relationship between these two representations. So when we measure a particle's position very precisely, it's like we're squeezing its position wave function, you know, making it very sharp and localized.
Oh.
But guess what happens to the momentum wave function at the same time?
Based on what we've talked about, I'm guessing it spreads out and becomes less precise.
You got it. The more we try to pin down the position, the less certain we become about the momentum and vice versa. It's a fundamental trade-off, and it's a direct consequence of how these representations are connected through that Fourier transform.
Fascinating.
It's like the universe is playing this game of quantum hide and seek with us, you know?
Right.
If you try to find the position, the momentum like runs away, and if you try to catch the momentum, the position just vanishes into thin air.
Yeah. It really does sound like at the quantum level, reality is inherently fuzzy.
Yeah.
It's a humbling thought, isn't it? That, like, there are these fundamental limits to what we can know with absolute certainty.
It is, and it really challenges our classical intuitions about how the world works, you know?
Right.
But within this uncertainty lies this remarkable elegance and this symmetry.
Okay.
Let's explore this a little bit further by looking at a classic example, the free particle.
Okay, yeah, I remember we touched on that a little bit earlier.
Yeah.
That's a particle that's just cruising through space. right? Not subject to any, like, external forces or anything.
That's right. It's a simple system, but it beautifully illustrates the interplay between these position and momentum representations.
Okay, cool. So how does the free particles quantum state evolve over time? Let's start with the position representation.
All right, so imagine you have like a snapshot of the free particles wave function at a particular moment.
Okay.
It might be a nice localized bump, meaning we have a good idea of where the particle is.
Okay, I can picture that sort of like a ripple in a pond after you drop a pebble in.
Exactly.
Yeah.
But as time goes on, that ripple starts to spread out,
Uh-huh.
the wave function expands, and the particle's position becomes more and more uncertain.
So even though it's moving at a constant speed, we become less sure about where it is as time goes on.
Precisely. It's like the particle's position is slowly like dissolving into this cloud of possibilities.
Wow.
But here's where the momentum representation provides a really fascinating contrast.
Okay, let's flip the coin then and see what's happening over in momentum land.
Okay, so in the momentum representation, the free particle's wave function is this sharp, well-defined peak, reflecting its constant momentum, and as time goes on, this peak stays put.
Uh-huh.
It doesn't spread out like the position wave function.
So it's a picture
Yeah.
of perfect stability in the momentum world, while over in position world, things are getting fuzzier and fuzzier.
That's a great way to put it. And this difference really highlights the beauty of having these different representations.
Yeah.
You know, they each provide a unique lens through which to view the quantum world.
It's like having two sets of glasses.
Yeah.
One that lets you see the particle's position and another one that reveals its momentum.
Precisely. And by switching between these perspectives, we can gain a much richer understanding of the quantum world.
Right.
It's like appreciating a piece of art from different angles, you know?
Yeah.
Each viewpoint offers a new insight.
I'm really starting to see how these representations are more than just mathematical tools.
Yeah.
It's like they're windows into the very nature of quantum reality.
That's a very insightful way to think about it.
Yeah.
They force us to reimagine our classical notions of definiteness and certainty, you know?
So we've explored these two main ways to describe quantum states, position, and momentum representations.
Right?
We've talked about how they're connected through the Fourier transform
Yeah.
and how this uncertainty principle emerges from their interplay.
Yeah.
It's been a mind-bending journey so far.
It is, and this is just the tip of the iceberg, you know?
Oh, really?
There's a whole universe of fascinating concepts and phenomena waiting to be explored.
I'm eager to dive in deeper. What other mysteries of the quantum realm are waiting to be unlocked?
Well, one thing that often comes up is how these representations are actually used in practice.
Okay.
We've talked about them in a somewhat abstract way.
Right.
But how do they help us solve real problems in quantum mechanics?
That's a great question. I'm curious about that too. Can you give us some like concrete examples of how these mathematical tools are actually put to work?
Absolutely. Let's take the example of the hydrogen atom.
Okay.
It's the simplest atom with just one proton and one electron.
Okay.
But its structure and behavior are governed entirely by quantum mechanics.
Okay, so how did the position and momentum representations come into play when we're trying to understand the hydrogen atom then?
Well, imagine trying to describe the electron's behavior around the proton, you know?
Okay.
In the position representation, we'd be looking at the probability of finding the electron at various locations around that nucleus.
It's like creating this 3D map of the electron's possible whereabouts within the atom.
Exactly. And this map would reveal something fascinating. The electron doesn't just exist at any random point.
Oh.
It's confined to specific regions of space, forming what we call orbitals.
Oh, yeah. I remember hearing about orbitals in chemistry class.
Yeah,
They're those oddly shaped clouds around the nucleus, right?
that's right. And those shapes emerge directly from solving the mathematical equations that govern the electron's behavior in the position representation.
So the math actually predicts the very structure of the atom.
It is, and the momentum representation plays a crucial role as well. It helps us understand the energy levels of the electron within the atom.
Energy levels. So that's why electrons can jump between different orbitals, absorbing or emitting light in the process.
Exactly. The momentum representation provides a framework for calculating these energy transitions,
Okay.
explaining why atoms emit specific colors of light.
So these representations aren't just theoretical abstractions then.
Right.
They're powerful tools that allow us to actually calculate and predict the behavior of real physical systems.
Precisely. They're the foundation upon which our understanding of the quantum world is built.
It's like we've learned the alphabet of quantum mechanics, and now we're starting to write sentences and tell stories about atoms and particles.
That's a wonderful analogy. And as we continue to explore this fascinating field, we'll discover that the stories of quantum mechanics are full of surprises and mind-bending plot twists.
Yeah, it's amazing to think that these mathematical representations like position and momentum, they're not just these abstract concepts, but they actually have these like tangible consequences in the real world, right? They shape the structure of atoms and they influence how light interacts with matter.
That's right. And we haven't even scratched the surface of their applications. These representations are essential for understanding a wide range of phenomena, from the behavior of electrons and semiconductors to the properties of these exotic particles like quarks and neutrinos.
It sounds like we've just opened the door to like a whole new universe of exploration.
Yeah.
What other insights can we gain from these representations?
Well, one area where they really shine is in helping us understand how quantum systems change over time. And this brings us to another key player in quantum mechanics, the Schrödinger equation.
Ah, yes. The Schrödinger equation.
Ah.
I remember hearing about that. It's the equation that governs the evolution of quantum states, right? Kind of like how Newton's laws describe motion in classical physics.
Exactly. The Schrödinger equation tells us how the wave function of a quantum system changes over time.
Okay.
And it turns out that the equation takes on different forms depending on which representation we choose, like position or momentum.
So it's like the equation adapts to the language we're speaking,
Right.
whether it's the language of position or the language of momentum.
Precisely. And the choice of representation can actually make the equation easier or harder to solve depending on the specific problem we're tackling. Sometimes the position representation is more convenient. Other times the momentum representation simplifies things.
It's like having different maps for navigating the quantum landscape.
Yeah,
And some maps are definitely more user-friendly than others.
that's a great analogy. And choosing the right map, the most appropriate representation, is often the key to unlocking the secrets of a particular quantum system.
Okay, I'm starting to see how powerful these representations can be.
Yeah.
But can you give us the concrete example of how the Schrödinger equation works with these different representations?
Sure, let's go back to our old friend, the free particle.
Okay.
Remember, in the position representation, its wave function spreads out over time, right? Reflecting that increasing uncertainty in its location.
Right.
Well, the Schrödinger equation in this representation beautifully predicts exactly how that spreading happens. It gives us this precise mathematical description of how the probability distribution evolves over time.
So it's like we're watching a movie of how the particle's position becomes fuzzier and fuzzier, even though its speed remains constant.
Exactly. And in the momentum representation, the Schrödinger equation predicts, well, no change at all, because the particle's momentum is constant. Its momentum wave function remains that sharp peak forever frozen in time.
That's so cool. It's like the equation itself confirms what we already knew intuitively about the free particle.
Precisely. And this is just one example.
Right.
The Schrödinger equation, in conjunction with the appropriate representation, can be used to calculate and predict a wide range of quantum phenomena. It's one of the most powerful tools we have for understanding the microscopic world.
It's amazing to think that we can use these mathematical tools to like delve into the heart of matter, to understand how the tiniest particles in the universe behave. It's like we're unlocking some secret code that reveals the hidden workings of reality.
It is truly remarkable, and what's even more fascinating is that these representations and these equations are not just about calculating numbers. They force us to confront these profound questions about the nature of reality itself.
What do you mean?
Well, if these different representations, position and momentum, are just different ways of looking at the same information at different sides of the same quantum coin,
Right.
what does that tell us about the nature of the quantum world? Does it even make sense to talk about a particle having a definite position or a definite momentum before we measure it?
Those are some deep questions.
Yeah.
And they really highlight how quantum mechanics challenges our classical assumptions about how the world works.
It does indeed, and I think that's what makes it so captivating. Quantum mechanics is not just a set of equations and rules. It's a journey into a realm where our intuitions break down and we're forced to reimagine the very fabric of reality.
Yeah, I have to say, this whole deep dive has been an incredible journey. We've gone from the basic concepts of quantum states to exploring these powerful mathematical tools that allow us to make sense of the quantum world.
I'm glad you found it insightful, and I hope it encourages you to continue exploring this fascinating world of quantum mechanics.
Yeah, absolutely.
There are still many mysteries to be uncovered, and who knows what mind-bending discoveries lie ahead.
Well, thank you so much for joining us today. It's been an absolutely fascinating conversation.
It's been a pleasure.